Okay, so today we're going to talk about partial differential equations, which can be abbreviated by PDE. Okay, so what is a PDE? So it's obviously a differential equation. PDE is a differential equation whose solution depends on at least two parameters Okay, so basically it can be x, y, or x time, and so on, okay? So depending on the form of the problem, meaning boundary conditions, initial conditions, basically, and most important, the system is linear, non-linear. Different techniques may be used to solve the partial differential equation. So these methods are the most common one, and that's the one we're going to cover today, is the separation of variables. Okay, SV. Then one that I mentioned before is the variation of parameters. Three would be the, okay, now we have the Laplace transform, mostly used in controls and electrical engineering. For the Fourier transform, five, some complex solution. This one is for sustain periodic problems. Six is the Duhamel's method for time-dependent boundary conditions. And let's say, I mean, there's more, but let's look at the Green's function or Green's functions here. So basically, if you look at all these ones, except the Duhamel and the complex solution, separation of variables, variation of parameters, Laplace transform, Fourier transform, Duhamel's Green's function is basically how you assume the form of the solution, and then you go through a different method. Okay, So let's look at the first one, which is the separation of variables. So separation of variables was kind of developed by D'Alembert, which was a French mathematician, Bernoulli from Switzerland, and Euler from Germany. Okay. Probably you know the D'Alembert principle, which is for dynamics. When you do all the forces, the summation of forces minus ma equal to 0. But again, so let's see the requirements. In order to be able to use the separation of variables, you need first to identify a few things within the PDE. So first it needs to be a linear problem, meaning that the PDE and boundary condition must be linear. Alright? Then the geometry, and this is important because of something you will see later called the orthogonality condition, must be contained within an orthogonal, and that's because of the orthogonality condition, orthogonal reference frame. Okay, and this is the most important. No more than one non-homogeneous boundary condition or initial condition. Okay, but this is not really a big problem, as you will see, because we do at the end by using the principle of superposition. You can just break the problem into multiple problems that we only have one non-homogeneous boundary condition or initial condition. All right. So let's go and let's do one example. Alright, so this example is probably going to be long, so just wanted to give you the heads up. So the example would be from heat transfer. Alright, so over here let's say steady state, which means what? dt equal to 0, so steady state, heat conduction with constant thermal conductivity okay, and without any heat generation. Okay, so basically the equation is what is the gradient of K delta T plus, let's say this is some heat generation, will be Q, will be equal to rho C delta T over delta T. But since we know is steady state this is equal to 0. Alright, there is no heat source, no heat generation, and then we say that this here was constant, so that means that we can move it outside the gradient. Okay, and K here's what is the thermal conductivity. So that means that this equation actually becomes what? K, if you remember when you do the dot product, this does not become a vector, it becomes a scalar, so we get the Laplacian operator of the temperature, and this is in function, that is of T, then this is equal to 0, or we can just rewrite this if you divide by K both sides. This is equal to 0. Okay, so for a 2D problem, which is the one we're going to use, what do you have? So that means that T would be in function, let's say, of xy. So the Laplacian equal to 0, which means that partial derivative of xy partial x squared plus partial derivative of t xy partial y squared will be equal to 0. Okay? So this is the PDE that you see is in function of two variables x and y. Okay, and it's linear. So now let's do the problem. We need to look also at the boundary conditions. So in this problem, we're going to consider something that is orthogonal, which would be, let's say, just a rectangular plate, and we want to calculate what is the temperature distribution on the plate. So we select our orthogonal reference frame, that would be x and y, and now we need to specify, so let's say that this would be a length L and height h. Okay, so let's say we need to have homogeneous boundary conditions. So let's say this would be 0 here. Okay, maybe we can put let's say that is 0 over here, so it's homogeneous. That is 0 over here, and then over here we're going to say that t basically will just be in function of x, because it's along only the x direction, not the y. So again, we only have one non-homogeneous boundary conditions. So this homogeneous this boundary condition can be written as what? So let's see, t of 0, so let's look at this one, will be t of 0 y is 0. Did this one, now this one, this would be t of L y is 0. So we did it on this direction, which is both of them are homogeneous. Now let's do it on this direction. So t of x at y equals 0 would be along this line is 0, and t along x at h will be equal to f of x. Okay, so basically over here we see that all the boundary conditions are homogeneous except for one. So there's only one non-homogeneous boundary condition. Okay, so that means that we can apply the separation of variables. So use separation of variables technique. Okay, so here we go. So really the only thing that the separation of variables technique has is to do the following. So this would be page 207. So the main technique is, the first thing is to do what? To assume the solution of txy as being equal to what? To a function of x, which is just in function of x, times a function of y that is just in function of y. Okay, so that's it. And now we just follow the normal procedure. So over here, what do you see? This is only in function of x, this will only be in function of y. So now we do this, what does that mean? We're going to have delta, so partial derivative of t with respect to x will be equal to what? Partial x of x y of y. So this will give you what? This is only in function of x, will give you partial of x divided by x times y of y plus x of x partial of y divided by x. But since we know that this is only in function of y, this will be 0. So now the second derivative of the derivative with respect of the temperature with respect to x will be partial x, and we do exactly the same thing of what? Of partial x of x divided by x, y of y. So it will be equal to the second derivative of x with respect to x squared, y of y plus partial x of x partial of y with respect to x. And as before, this term will be equal to 0. So basically what we have is that second derivative of t with respect to x squared would be equal to what? Second derivative of x squared times y of y, or I can just rewrite this as x second derivative times y. Okay? If you want, you can put here of x and this of y. Okay, so similarly, you could get what? That the second derivative of t with respect to y squared will be equal to second derivative of y with respect to y squared times x of x, or will be double y of y times x of x. So you remember that's the same thing we have been doing for the one order differential equations. Okay, and so what happens now is that you substitute into PDE. So what do you get? You get that so this equation is the PDE, would become what? Would become x double dot of x times y of y plus y double dot of y x of x equal to 0. Okay, so that means that x double dot of x y of y equal to minus second derivative of y x of x. And now you will see why they call this method separation of variables, because what you need to do now is what? Separate the variables. Okay, so you're gonna get x double dot x over x of x. Okay, let's say will be equal to minus y of y double dot of y of y. So now what do you have? You have this side is only in function of x, and this one over here is only in function of y. So the whole idea is to solve two different ODEs, okay? One second order ODEs, one would be in function of x, and the one would be in function of y. But in order for this to be valid, both needs to be equal to and to a value over here to let's call this one, let's put in red, to lambda square, and this is the eigenvalue. Okay, so over here is when sometimes students get a bit confused. Okay, this is an eigenvalue. So the whole thing over here is, let me go get the first page. The strategy is to first solve the boundary value problem in the direction where you have both homogeneous boundary conditions. So that will mean we need to solve it on the x direction. Okay, so now it depends how you want to define the boundary value problem. So if we define the boundary value problem as being equal to, okay, let me write it down. So let me keep that page over here. So 208. Okay, let me just go a bit back, because I think more than the accuracy here, the concept is almost more important. So now over here, and then we can change the sign. The whole thing over here, you have this ratio and you have the lambda over here, okay? So we can set up over here. From here, you can get two different second order ODEs. Or so this become what? You're gonna have x double square over x of x will be equal to lambda squared. So this will give you a first problem over here that will be what? X double dot of x minus lambda square of x equal to 0. Okay, so that's what the thing comes from different textbooks, but it really should not matter. Okay, so basically, generally the boundary value problem is defined as what? It's defined as a problem being equal to x double dot plus lambda the eigenvalue, and here should be really a plus. So in order to have a plus here, but again, it should not matter at all, you would just have to add a minus sign over here, meaning that now you will have here this minus sign. So once you move to the other side, this becomes, oops, sorry, so you have the minus sign, so when you move it to the side, this becomes a plus. So this would be our first problem over here, boundary value problem, for which we need to define now the so we have this problem, which is a boundary value problem, and we say this would be on okay, so this would be 0 here, 0. So we solve the problem in the x direction. Okay, that's the problem we are doing here. So the boundary condition and direction were what? If you look at the boundary condition in that direction, let's see, I don't have the page, let me move the page. So we had that, let's just rewrite them down. So t of at 0 y was equal to 0. Okay, so this is, we are just using x, which is just in function of x, so we only use this one. So this means we can rewrite the boundary condition as x of 0 will be 0, and then the second boundary condition is what? T at L of y is also equal to 0. So this will mean what? This is only in function of x, so x at L will also be equal to 0. So basically the first thing we need to do is solve the boundary variable problem, this one here with these boundary conditions. And now we just go back as if it was a second order ODE. Okay, so basically we're going to solve two different ODEs, and then we'll solve the other ODE that will be given by the equation with the minus sign. Okay, so we'll solve this one here. So then this will become what? Y double prime minus y will be equal to 0. Okay, so this is the first problem we need to do, solve these boundary variable problems. Let me maybe write it down here. So this is the first problem, and we can have what? We'll have y prime of y divided by y of y will be, so it's minus here, will be equal to minus lambda square, which will give us the problem of y. So this will cancel out the minus sign, and then we'll have minus lambda of y equal to 0. So now we'll solve this problem over here, okay, with what boundary conditions? On this one we need to move here up on the y direction. All right, so what do we know? We know t here was equal to 0 and t here was equal to f of x. So we need to solve this problem with the conditions of what? T of x0 will be equal to 0, and t of xh will be equal to f of x. Alright, so this will give us what? This will give you that y at 0 equals 0, and this will give you that y at h will be equal to fx. So that's basically the whole thing. And then from here you're going to find a solution f of x of x. From here you're going to find a solution y of y. And then what will be the solution? You will substitute into the assumed solution, which is, I'm missing here just that page, where is you will substitute it into the assumed solution, and this will be the final solution. Alright, so now it's the part that is a little bit tedious. So 7 to 8 is that we need to solve the two problems. So let us solve boundary value problem first. Okay, so this means we need to solve the x double dot, plus lambda square x equal to 0 with the boundary condition. So this is this will be now our ODE, okay, or better just say this one boundary value problem with the initial conditions x of 0 equal to 0, x at L equal to 0. So again, here we follow the same procedure. Within this one, what you need to do first, assume the solution. So let's say assume solution. Let's say it will be of the form, letter x would be, let's say, x sub naught e of mx. Okay, so this will give us that x prime would be equal to what? X sub naught m e mx. X double dot equal to x sub naught, which is a constant, m square e mx. So same procedure as before, okay? Always the same procedure. Now what do? You substitute into boundary value problem. So what you're gonna get? You're gonna get, I'm gonna start going a bit fast. If you factor out by the x sub naught E mx, the x double dot will give you the m square, and then this will be x is outside plus the lambda square would be equal to 0. And if you remember, what's the name of this equation? This should be the characteristic equation. So when is this equation satisfied? Either x sub naught equals 0, which yield to the trivial solution which is of no physical interest, or when what? Or when m square plus lambda square equal to 0, okay? Which is what we are interested. So now here we need to solve this equation, and we need to see what happens for different signs of lambda as we did before. So let me go to the next page. And let me just recall that equation. So we have the equation. We need now to solve the m square plus lambda square equal to 0. Okay? So we're going to look at different cases. So let's say case 1. We're going to look at when lambda is negative. So it's less than 1. So in that case, what do you have? You have m squared plus lambda squared equal to 0, which means that m squared equal to minus lambda squared, which will give you what? That m will be equal to so this is negative. Oh, you see this is negative, so this then becomes positive. Okay, this negative, the negative will become positive, so this will mean that okay, so this is equal positive lambda square because lambda is negative. Okay, so this will mean that we are on the case that m will be equal to m squared, that m will be equal to plus minus lambda. So now I remember what is our assumed solution. What's this one over here? So following the procedure, that will mean that the general solution for this case of x will be equal to c1 exponential lambda x plus c2 exponential minus lambda x. Okay, so now we go through some algebra using Euler's relations, which to relation that E of theta equal to cos theta plus sinh of theta, and I minus theta equal to cos of theta minus sinh of theta. So I just substitute over here. So this means that x of x will become what? Becomes c1 cos of, so this time this will be delta x plus sinh delta x. So it will be the first term plus c2 of cos delta x minus sinh delta x. So this will give you that the first solution, we still have some algebra, will be equal to C1 plus C2 cos lambda x plus C1 minus C2 sinh of lambda x. And let's just say that we can write this as x of x equal to C1 bar cos of lambda x plus C2 sinh of lambda x, where C bar 1 will be C1 plus C2 and C bar 2 will be C1 minus C2. Okay, so now if this is a solution, this should also satisfy the boundary conditions that we have. So the two boundary conditions were what? And these ones over here, x of 0 equal to 0 and x of L equal to 0. So let's say if this solution will satisfy the boundary conditions. Okay, so let me maybe just rewrite the equation. So we have x of x equal to C1 cos lambda x plus C bar 2 sinh lambda x. So in order to understand the solution, what we need to do is a little plot over here of the two functions cos and sinh. So basically the function sinh is this way, okay, and the cos function will cut the y-axis at a point 1 and we'll do some type of an parabola this way, okay, and this will be the cos function. Alright, so let's see what happens. If we need to have x of 0 equal to 0, what would that mean? At 0 we know the sinh will be equal to 0, so we'll have C bar 1 cos of lambda x must be equal to 0, which is only possible if C1 bar is equal to 0. So now let's see what happens for the second one. X at L, which is at the other side of the plate, is also be equal to 0, so this will mean that C2 sinh delta L should be equal to 0. Okay, and we know that this is only possible here. The sinh can only be 0 and if this is equal to 0. Okay, and we know this is equal to a constant. So simply this is not possible unless C2 is also equal to 0, which will be the trivial solution. So again, let's say this is different than 0 at point L. So the only possible solution is if C2 equal to 0, which is the trivial solution, which is of no interest. But again, this is not really possible, okay? So let's write right here, not possible. So again, then this is not a valid solution. So we need to go then to case 2, where this time will be when lambda equal to 0. Okay, so if lambda equal to 0, let's recall the initial equation. So we have x double dot plus lambda x equal to 0. So if lambda equal to 0, this is equal to 0, which will mean that x double dot equals to 0. So x dot will be equal to, let's say, a constant. So let's say it will be equal to 0. So this would mean that if we do the first integration, this would be equal, we use C1, C2, so let's say it will be equal to a constant C3. And then the last solution, f of x, will be equal to what? C3x plus C4. Okay, so now this could be our solution. So let's see if that will satisfy the boundary conditions. So we mean x of 0 equal to 0, which means what? C4 will be equal to 0. Okay? Then if x of L equal to 0, this will mean that C3L must be equal to 0, where this is only possible if C3 equal to 0. So that means that we have C3 equals C4 equal to 0, which is trivial solution. And as we said before, no physical interest in that solution. So now, obviously, we're going to go to the last case, which would be the appropriate one, will be case 3. This time is for what? Will be for lambda positive. So for lambda positive, what do we have? So let's say we have the x double dot plus lambda squared x will be equal to 0. So in that case, after substitution, what do we have? We have the equation that m square plus lambda square was equal to 0. So now this will mean that m square equal to minus lambda square, and now lambda is positive. So this will mean what? That m will be equal to plus minus I square root of lambda square, which will be lambda. And again, I have bad luck, so that means that the assumed solution here, remember, is always, the assumed solution is always of the form x was x naught e lambda x, okay? So the assumed solution in this case will be x of x will be equal to, let's say we'll have c5 exponential of I lambda x plus c6 exponential minus I lambda x. So basically this is our solution that we want to remove the imaginary notation. So for that we're going to use again the Euler identities. So using Euler's identities, so for imaginary numbers, where you know that e I theta will be equal to cos theta plus I sin theta, and e of minus I theta is equal to cos theta minus I sin theta. So we substitute it into the previous equation. We're going to have x of x. So remember, this is our previous solution. So we're going to have c5 of cos lambda x plus I sin lambda x plus c6 cos lambda x minus I sin lambda x, which will give you that x of x is equal to C5 plus C6 cosine lambda x plus C5 minus C6 I sine lambda x, or you could just rewrite this as x, let's say, will be equal to C5 bar cos of lambda x plus C6 bar sine of lambda x, where you have the C bar 5 will be equal to C5 plus C6, and the 6 bar 6 will be equal to C5 minus C6 to the I. Okay, so now this should also satisfy the boundary conditions. So let's go. So we know that we need to have x of 0 equal to 0. So this will give us what? C5, because cos of 0 is 1, so C5 1 plus C6 sine so of 0, basically this will be 0. So from here this needs to be equal to 0, so this can only happen if C bar 5 is equal to 0. Here we go. And second boundary condition is x at L equal to 0, so this will give us what? So we know C5 is already 0, so this will give us C6 sine of lambda L must be equal to 0. So again, this is satisfied if C6 is equal to 0, but that is a trivial solution, so it's of no interest. Or, so this will mean that sine lambda L, so let's see here, C6 equal to 0 will be trivial solution, which is of not interest. Or we'll have sine of lambda L that will be equal to 0. So then, when does that happen? So remember the circle over here, trigonometric circle. You know that the sine will be 0 where? Sine will be 0 here and here. So this is, let's say, 0, pi, and so on. So that will mean that sine lambda L will be equal to 0 when lambda L will be equal to what? N pi. Okay, where n is a natural number, cannot be a decimal number. It needs to be 1, 2, 3, 4, 5. Okay, so if you do this, this will mean then that lambda is equal to n pi over L. Okay, so what does that mean? So that the solutions, so that we're gonna have x of x, all right, will be equal to what? So we know that C5 is 0, so we'll have C6 sine of lambda x, but what is lambda is n pi over L, so that will mean that x of x will be equal to C6 sine of n by x over L. Okay, so now if you remember the principle of superposition, states what? That if you know a solution y sub 1 and you also have a solution y sub 2, and let's say any type of solution, if you add them all together, that will also be a solution y. So imagine that you have different values for C6. So that means that if you do C6 equal, let's say instead of 6 or n equal to 1, so let's say replace the 6 by an n. So we'll have C bar 1, this will be a solution, C2 will be a solution, C3 will be a solution. Okay, so that will mean that we could rewrite this solution here, x of x, as being equal to the summation of all the different solutions from 1 to infinity of C sub n, okay, sine n pi x over L. So here we go. So now we found the first solution, the first part of the solution to the assumed solution, which is, let's see, which is this one over here. So now we need to find y of y, and in order to find for y of y, we need to solve now the second problem, which will be to solve this one over here. Okay? So next, let's solve the equation this one here that we have, minus lambda square of y equal to 0, that had the boundary conditions. Okay, so I think was at the bottom, so with the bottom will be what? Will be I don't know if we did it before or if I needed to redo it here. Let's go back. Alright, almost there. Okay, we already specified the boundary conditions for that one as well. So it's this one over here with y of 0 equal to 0, y of h equal to f of x. So we need to solve this one with the condition y of 0 equal to 0, and the other one is y of h equal to fx. So these are the boundary conditions. Okay, so basically now we know that we only need to solve for lambda positive, okay, because the other ones will not be solutions of the other one. Okay, so again, all right, same procedure is assume solution to be of the form solution to be of the form, let's say y of y would be equal to y naught e n of y. Okay, so y prime, I'm going to remove the y, would be equal to y naught n e of ny. Y double dot will be equal to y naught n square e of ny. Then we substitute into ODE, which is this one over here. So what do we get? We're gonna, if we factor out by y naught e y and y, this will give us what? n squared minus lambda squared will be equal to 0. So once again, if y0 is equal to 0, this gives the trivial solution, which is of not physical interest. Or you can have n squared minus lambda squared equal to 0, which will mean that n squared equal to lambda squared, and we know now it's positive, so this will mean that n equal plus minus lambda. Okay, we substitute into the assumed solution, and this will give you what? So this gives you that we have the solution of y. Let me change the constant, let's say d1 e lambda t plus d2, not t, y, d2 e minus lambda y. Okay? So again, let's say using Euler's relations, E of lambda equal to cos theta plus sinh theta minus theta equal to cos theta minus sinh theta. So we substitute, we get y of y will be equal to what? d1 cos of lambda y plus sinh lambda y plus d2 cos lambda y minus sinh lambda y. So this will give y of y equals to d1 plus d2 cos lambda y plus d1 minus d2 sinh lambda y, or y of y will be equal, let's say, to d bar 1 cos lambda y plus d bar 2 sinh lambda y, where d bar 1 will be d1 plus d2, d bar 2 is d1 minus d2. Okay, but once again, now this function should satisfy the boundary conditions, which are what? The boundary conditions are y of 0 equal to 0, which means that I remember again the shape of the, so this will be the sinh function, and this will be the cos function. Okay, so we know the sinh will be 0, so this will give you d bar 1 cos of lambda 0, that will be basically 1, so this is 1, equal to 0, and this is only possible if d bar 1 is equal to 0. Okay, so that means that the second solution, the second boundary condition, which is y of let's wait for the second one. So this means that so that we have y of y will just be equal to d2 sinh of delta y. Okay? As previously, using the principle of superposition, that means that y of y, meaning that if you can add other different solutions, here we can have summation of n equal to 1 to infinity, let's say d sub n of sinh delta y will be the solution. Okay, I want to clarify one thing. Y over here, I don't go and apply the second boundary conditions. Because the second boundary condition, if you do remember, was at the end over here. So we had y equal to 0 here, and here y was equal to fx. So here is not homogeneous, so we cannot apply it. So just leave it under this form. And now we're going to use this condition in order to determine what will be those coefficients over here. Okay? All right, so the assumed solution for txy, which is what? Txy equal to x of x, y of y, will be equal to what? So we first do the one for the x of x, which was equal to summation of n equal to 1 to infinity. We had c sub n sine n by x over L. And now we just calculate the other one to be equal to the summation of n equal to 1 to infinity d sub n of sinh of delta y. Okay? So if you do remember from the previous calculations, we had that, I don't find it, but we had that lambda over here was equal to n pi over L. Okay? So basically that means that we can rewrite this solution here, let's say as summation from n equal to 1 to infinity. Let's combine the Cn and Dn into, let's say, constant E sub n. And now you have sine n pi x over L times sinh n pi y over L. So this will be our solution. Okay, if you want is the general solution, where this is not important here, but E sub n is basically C sub n D sub n. Okay, so now we go to the last step of this, is that to determine E sub n, the last boundary condition, basically the non-homogeneous condition must be used along the orthogonality property. So basically, yeah, I'm not going to mention it at the end. Okay, I don't want to confuse you. So basically, what was the last boundary condition is that t of at y of y was equal to f of x. So that was the boundary condition here. Okay, but this is h. All right. So what does that mean? So we substitute over here. This will mean that t, this is reversed. This is sorry, is x is all along x and is at h. So txh, so txh is equal to fx, but that will be equal to what? Would be equal to summation of n equal to 1 to infinity e sub n sine n by x over L times sinh of n by h over L. L is this side of the plate, and this is equal to fx. Okay, so what is the orthogonality condition? Put that one a different color. So orthogonality property instead of condition, yeah, property. Okay, so it's basically that integral along the length of the plate, let's say of sine n by x over L times sen, let's say another coefficient m by x over L dx. This is equal to 0 if m different than n and is equal to L over 2 if m equal to n. Okay, and now maybe I'm going to mention that. If you remember at the beginning we had the two equations that were equal to lambda. We had this page where we said everything was equal to lambda, so this was the eigenvalue, and basically if there's an eigenvalue we need to find the corresponding eigenvector. So what were the eigenvectors? So the corresponding eigenvector for the x problem is the sine, and the corresponding eigenvector for the y is the sinh function. Okay, so all the eigenvectors, okay, should obey the orthogonality property. Okay, so even the Bessel functions, believe it or not, are also eigenvectors, so they should also follow this property, but this is not part over here of the problem. So what we do next is just multiply this equation here by sine n by x over L on both sides and see what happens. Okay, we're almost done. So let's see, this will give us okay, so let's say recalling the equation we had before, t of x h is equal to the summation of n equal to 1 to infinity e sub n sine n pi x over L times sinh of n pi h over L, and this is equal to f of x. So what we do over here is that we're going to have that the integral 0 to L of e sub n sine n pi x over L. I'm going to now use this one, the sine n pi x over L times the sinh n pi h over L, but if you see this is a constant, so dx will be equal to the integral 0 to L of f of x sine n pi x over L dx. Okay, so you see right away that these two terms over here will be equal to what? These two terms will be equal to L over 2. E sub n is a constant, and this is also a constant. So this will give us what? We're gonna have oops, I removed the summation sign, which is fine. We can remove the summation sign because that's what we're trying to find. So this will give us E sub n times L over 2 sinh of n pi h over L will be equal to the integral 0 to L of f of x sine, and now let's say I just switch the m equal to n, so it's become n pi x over L dx. So this will mean that E sub n will be equal to 2 over L and then 1 divided by sinh n pi h over L of the integral 0 to L f of x sine n pi x over L dx. Okay, so now we know what E sub n is, so we can substitute it into our solution over here. Okay. Alright, so at the end we have the particular solution is what? Will be t of xy. Maybe let's just remember the general form was equal to what? Was equal to the summation and equal to 1 to infinity E sub n sine n pi x over L sinh n pi y over L. Okay, so let's just slightly rewrite it down. Okay, or we can say txy, let's say will be equal to the summations of n equal to 1 to infinity. Let me just call this a sub n of sine n pi x over L. Basically, I'm just substituting this one to make it a bit simpler. Okay, E sub n is 2 over L, 1 over the sinh. So what I'm going to do is put the sinh as part of the solution. So this will be now sinh n pi y over L divided by sinh n pi h over L. So that means that we took this one away. So a sub n will only be 2 over L times this function right here, where a sub n then is just 2 over L. If you see how the solution, we remove this one here, integral 0 to L of f of x sine n pi x over L dx. So this is basically the solution. So this is the particular solution. Okay, almost there. So very quick. Let's do an example. So example, if f of x equal to 1, then what does that mean? We have a sub n is equal to 2 over L integral 0 to L f of x sine n pi x over L dx. So this will be equal to, after integration, is 2 over L of cos n pi minus 1 divided by n pi. So if you think about it, this will be 0 if n equal to 1. This will be equal to minus 2 if it's equal to 2. Or the other way around. If you do the circle, here will be 0, here will be 1, no? Okay? So it will be here 0 minus 1, 0 minus 1. Anyway, so you can write this as a sub n is equal to minus 2 over pi to the minus 1 n minus 1 divided by n. Okay? And if you do the plot of this, so this is your plate, you should get some lines that which will be, so let me just put the center here. These lines are not that important. I'm just doing them to help me to show, but basically you have isotherms that will be lines going like this. Okay, so it will be the isotherms corresponding for different values of n. So just to show you what would be the temperature distribution, I did a little MATLAB code. I just programmed the solution. I think it's this one over here. Yeah. So basically you see this is the solution, Cn, sin n pi x with the sinh and sinh. And the other thing I do here is I put a time step of 0.1. So let's see what happens. And then we can make it smaller. So you see this will be the top. So this will be the change of the temperature gradient over here. Okay, on the grid. This will be the temperature. So you need to look at it if it was 1D over here. Now if I do this one here to let's say 001, it will be a lot more detail. So that's just what will happen here. Oh, okay, here we go. So this will be the temperature distributions over here. Okay, so, and just to finish, but this is extremely important, is that so let's say the solution of the problem of the walls not having homogeneous boundary conditions okay, can be obtained using the principle of superposition. So basically what I mean is what? Is that let's say you need to solve the problem the general problem you have here. Let's say the t over here will be equal to f1 of x. This will be equal to f2 of x. Here will be t equal to g1 of y, and here will be g2 of y. So you see all the boundary conditions are non-homogeneous. And you know that in order to use the separation of variables, you need to have at the most one non-homogeneous boundary condition. So the way to go around this problem is that you break this problem into three smaller problems. So in this case we'll have here, let's say you can use here, you can put here g1 of x, and then you use 0, 0, 0. You can put 0, 0, 0, use, so this will be y. You can put over here g2 of y. Then when you do the same thing with fx, you can put here f1 of x and 0, 0, 0. You can put here f2 of x will be 0, 0, 0. So the total solution here, the txy, which is will be the total solution txy, will be equal to what? Solution to this problem t1 xy plus t2 xy plus t3 xy plus t4 xy. Okay, and this will be the solution for the plate having non-homogeneous boundary conditions at all the different walls. Okay, so that would be it for today.